So before you learn anything about electron configuration, you need to know the following things. You need to know what the principal quantum number is. And you also need to know what the subshell is. And you also need to know what the amount of electrons, which will be represented as an exponent. So this would be 1, 2, 3, or whatever, like 2, 3, 1, or 3, 1, 2, doesn't matter. So let's say I have, for example, 4p3. This 4 here will be represented as the principal quantum number. This number right here will be represented as the subshell, and the amount of electrons will be this. So this is basically what an orbital is. How to use electron configuration on your chem helper. So here, you would look here and see how many boxes you have. See right here where it says 1s. There's one box and one box. So out of this whole row, which is period 1, also known as you would locate it as the principal quantum number. So this would be period 1, which would be principal quantum number of 1, period 2, principal quantum number of 2, period 3, principal quantum number of 3, period 4, principal quantum number 4, and so on. So here you only see hydrogen and helium, and there's only one box. In this whole row, all you see is 2s, because these two rows are part of the s orbitals. Then these 10 boxes and down, which are like 4 boxes down, so all these 40 boxes, this is all part of the d orbitals. So here would be D, 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 and so on. And now all over here, except for helium, it would be all part of the p orbital. So there are 6 p orbitals per period, or principal quantum number. So also there's S, D, P, and F, but we have not yet learned about F. So to do an electron configuration, you need to have your chem helper. And let's say you want to do an electron configuration for C, which is carbon. You would do 1s1, no, 1s2, my bad. Then you would do 2s2, then you do 2p6. Actually, if it's for carbon, then it would be 2p2, because it is, out of the 6 here, it is number 2. Next, we're going to learn about the valence electrons. Valence electrons are the electrons in the outermost energy level of an atom or element. These specific electrons are the electrons used for bonding. So I'm going to use an example to explain it to you, because that helped me. So if you look here, the 1 here represents the energy level, and the 2 here, the S, my bad, the S here represents the orbital shape. Then the 2 here represents the number of electrons. So to determine the valence electron, you want to find the highest energy level. So it's obviously not 1, not 2, it'll be 3. So you add the 2 exponents, and you get 8. 8 is the highest valence you can ever get. See, it'll work here again too. You want to find the highest energy level. So that's not high, not quite high, nope, no, no, yes, and no. So you look at the 4, and since it's only 2, 2 is your valence electron. Next, I'm going to talk about to diagram the electron configuration. So if you want to draw a diagram to show the amount of orbitals there are in, let's say, in neon, you are going to draw the amount of orbitals there are in the s orbital, 1s2, my bad. And there's only one, but then there's two elements. So these little arrows that must go down in different directions, which I'll explain later, represent the elements. So then you would also have to do the next two, then the next box, which represents the next two elements, which are S. So these two will represent the next arrows, so they must go in different directions. They will never be 2 arrows up and 2 arrows down. Then you'll go over here, and since there's 3 boxes, see, 1, 2, 3, you are going to draw 3 boxes. And since there are 2 elements that share a box, you are going to put 6 arrows, because there are 6 boxes with 6 elements. So that is to draw the diagram. About shorthand configuration. To do shorthand configuration for, let's say, a hard one and a long one for arsenic, you would go to the nearest noble gas, which is argon, and you would put here AR in brackets, and then you'll do anything else. You would continue. So K, you would put 1 box, which is up and down, or down and up, and then it was argon, so then you would do the 5 boxes next. You would do 5 boxes next. 1, 2, 3, 4, and you would do up, 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 down, 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 and then since arsenic is 3 out of 6, and you would put only 3 of those. That's for shorthand. Rule is for every orbital in a subshell is silently occupied with 1 electron before any orbital is doubtly occupied, and all electrons are silently occupied orbitals that have the same spin. So basically it's just when they have to go in two different directions. For Pauli's rule, that is when there is, for instance, these 3 represent Pauli's rule because there is not another one of these. I don't want to mess that up because that would give us another element. Pauli's rule is when there's only one single one and it can be in either direction. For Lewis structure, it's a little bit different because you need to find the amount of valence electrons there is before you can draw any. So going back to the valence electrons, let's say you need to find the valence electron for beryllium, which has actually 4 electrons. So you would draw beryllium as 1s2, 2s2. So you would take the largest one here, and since it has 2, that means there's 2 valence electrons. So when you draw the Lewis structure, it's going to have that, and you're going to draw that. And that is going to be your final Lewis structure. See? You only use 2 sides. You can only, since the highest number of valence electrons is 8, you can only go up to those. But that's not beryllium. That is a different element. About cations and anions. Cations are positive and anions are negative. Whoops. When this comes in handy to draw and do electron configuration boxes, let's say you want to do the diagram of the electron configuration of boron. So boron, the closest noble gas would be helium. So you would do the shorthand configuration, and it would be up, down, which is 2s, and then over here, which are 1, 2, 3, this would be the 2p, and since boron is the first one, that's going to be that. Boron also has a +3 charge on top, if you can see there, and you need to make it because it's missing 3, but here it's missing 5, so you would do this is all for boron, but this is for boron +3, and this is going to be that. This is going to be the answer. See how it's missing? 2, my bad. 2s and 2p.